Since 1990, the European Union has made significant progress in reducing greenhouse gas emissions, achieving a remarkable 32.5% reduction by 2022. But the journey towards a sustainable future is far from over. By 2050, the European Union has set an ambitious goal to become the first climate-neutral continent. To achieve this, up to 477 million tons of CO2 must be captured and used effectively. This is where carbon capture, utilization or reuse plays a crucial role. CCU is a set of technological solutions that involves capturing carbon dioxide emissions from sources like industrial plants and power stations, and then converting the captured CO2 into value-added products or alternative energy sources. Photo2Fuel project is working towards advancing CCU technologies using CO2 as feedstock and solar energy as power source to produce clean fuels and chemicals based on the concept of artificial photosynthesis. But what exactly is artificial photosynthesis? In nature, photosynthesis is the process by which plants convert sunlight, water and CO2 into oxygen and energy-rich molecules. Artificial photosynthesis is an emerging technology that, mimicking natural photosynthesis, captures CO2 and water molecules, efficiently converts them, and creates valuable organic molecules with the help of solar energy. In Photo2Fuel, artificial photosynthesis happens in biohybrid systems, an interesting new approach that brings together the powerful, selective capabilities of microorganisms with efficient, human-made light harvesting materials. At the heart of Photo2Fuel's biohybrid systems are two microorganisms, Mirella thermoacetica and Methanosarcina barkeri. Mirella thermoacetica is a bacteria known for its efficiency in converting CO2 into acetic acid, a key ingredient in many industrial processes under anaerobic conditions, which means in the absence of oxygen. Acetic acid is essential for producing plastics, textiles, and even food additives. On the other hand, Methanosarcina barkeri is an archaea that produces methane from CO2, also under anaerobic conditions. This methane can be used as an energy source, similar to fossil gas. But these microorganisms alone are not enough. To unlock their full potential, we need to harness the power of sunlight. This is where photosensitizers come into play.
The photosynthesizers which we are working on are of organic origin. So we use this specific hybrid system to put them on, as to say, on the microorganisms. The photosynthesizers are specific designed that they can attach to our organisms and that they will harvest the light. So in a special way, the light will go to our photosynthesizers, and then the electron pathway will go on, and the electrons, our protons, will go further in our metabolism of the specific microorganism used in the Photo2Fuel project.
Think of photosensitizers as the spark that ignites the whole process. Without them, the sunlight that powers the system couldn't be effectively used by the microorganisms. In the Photo2Fuel project, photosensitizers are carefully chosen to efficiently capture light, transfer the generated energy directly to the microorganisms, and stay closely connected with the bacteria, enabling CO2 utilization. In the Photo2Fuel project, we use organic photosensitizers that can be easily engineered to have specific light absorption properties and more environmentally friendly due to the absence of metals.
In our lab, we are culturing different archaea strains. For the Photo2Fuel project, we are focusing on the Methanosarcina barkeri. In our project, we try to add the specific photosynthesizers to the Methanosarcina barkeri and check whether they are producing under this specific conditions with sunlight and CO2, they produce methane. For this, we have to check, of course, the specific living parameters for the barkeri strain. and we have to check the culture medium for the parameters. We have to check the light intensity, light spectrum, for example. And of course, we have to check whether they are producing methane or not. This we are doing mostly via the gas chromatograph. And we check, for example, the viability of the microorganisms via fluorescence microscopy.
As we continue our research, Photo2Fuel is preparing to scale up the most efficient system, ensuring we can move from the lab to real-world applications. This means refining separation technologies and conducting sustainability assessments, taking into account the environmental, the economic, and the social perspectives.
Renewable energies are really important nowadays and also in future. We want to reduce the CO2 and we want to get rid of or make substitutions of the fossil fuels, for example. So on the one hand, we use a lot of wind and solar energy, for example, which it's not so easy to store. On the other hand, we have a lot of CO2 production, which we also want to reduce. This in combination, and to have a look on the Photo2Fuel, we can combine this. We can use the sunlight, so the energy from the sun directly, and we can use the CO2 from different sources and combine them in our reactor and in the hybrid microorganism system to produce renewable methane, which can be used in every application as the fossil fuels, for example. Or in the other way, we can also produce acetic acid, which we can use as a renewable acetic acid to produce as a basic chemical.
As we look towards a future of clean energy and sustainable industries, projects like Photo2Fuel are valuable steps forward. By transforming CO2 from a problem into a resource, this project joins the collective scientific effort to address climate change. Together, these innovations are paving the way for a world where technology and care for our planet go hand in hand.